In this video, we're going to introduce the idea of aromatic molecules. Aromatic molecules are very special. They are a new classification of organic molecules. So we started off and we said that organic molecules can be broken down into two groups. Aliphatic, and we said that aliphatics could be broken down into saturated or unsaturated. But organic molecules can also be aromatic. And so the either or question that follows that is this molecule aliphatic or aromatic? They don't usually try to split the hair of is aromatic saturated or unsaturated. And I'll try to explain why that is, because essentially it is kind of like a saturated molecule and kind of like an unsaturated molecule. It appears to have multiple bonds from the number of carbons and hydrogens, but it doesn't react or behave like it has double bonds. So it reacts more like a saturated molecule, yet it's empirically got some unsaturated properties as well. So aromatic molecules get their own classification. And essentially, all aromatic molecules are going to have a benzene ring. And so a benzene ring is a 6-carbon ring that has the appearance of having alternating double bonds. And they're not really actually alternating double bonds, but the formula C6H6 is specific to the benzene ring or the phenyl ring. So the benzene ring is when it's a parent chain and the phenyl is when it's being a branch. So I'll use those two words, and they're not technically interchangeable, but they're talking about the same kind of a structure. It's the aromatic ring. The aromatic ring is a parent chain and the aromatic ring as a branch. But as long as it's got a benzene ring in it or a phenyl branch, it is an aromatic molecule. Benzene doesn't actually really have alternating double and triple bonds. So some people try to explain that like if we had the double bonds here, it's like it's switching back and forth between that and this instantaneously. So it's like those double bonds are constantly moving around, and so they'll call that kind of a delocalization of electrons. But realistically, it's not actually a difference in bond or a different single and double bonds. In fact, what it's really more like, and so we'll see this drawn quite often, is that the 6 carbons in that ring are sharing the electrons equally all the way around. And so those electrons are being shared equally, and the bond length between any 2 carbons in this benzene ring is the same. And so earlier on we'd said that single bonds tend to be longer and double bonds are a bit shorter, but when we actually measure that on the benzene ring, we find out that they are the same, so that there's the same bond length between each of the carbons. And so it suggests that it's actually not really got any double bonds. It's got these electrons delocalized all the way around the carbon. And so it makes it extremely stable, because in an alkene where you've got a double bond, like if this was an actual alkene, those carbons are brought closer together, and it takes less energy. It's a little bit more favorable to break that double bond. But when you've got a benzene ring, when you've got the benzene ring, it's actually not easy to break a single double bond, because you'd actually need to break all of those double bonds and shift the electrons around. So the benzene ring is very stable. It's much less reactive. If I had a molecule that had 3 double bonds, it should be really reactive. But aromatic molecules are very stable, and so we have this idea of these electrons being delocalized all the way around. And so this is probably a bit more of a realistic image of what is really going on with the electrons in an aromatic ring. So the aromatic rings behave more like they have extra bonding electrons being shared by all the carbons, and this is called electron delocalization. And when I typically draw a benzene ring or a phenyl ring, I'm going to draw it like this, where I've got the 6 carbons forming the hexagonal ring structure, and then I'm going to draw those electrons being delocalized like this. But they don't have to be. Like, it would be reasonable to draw it like this. It would be reasonable to draw it like this, right? Like, this is a fair way to draw it, so is this and this. So don't be thrown off if you see it that way. And it is not uncommon to see it shortened to C6H6, or if it's being a branch, it'd be C6H5 bonded to something. The benzene rings, we're going to go into how you name them in a separate video, but the behavior of these molecules is all down to that really stable structure and the delocalization of electrons.